So if you've ever tried to temper chocolate in your kitchen or maybe, cook a steak sous vide, you probably already understand this really fundamental rule of thermodynamics, which is that temperature is literally everything.
Oh, absolutely. Yeah, it really is.
Right, because when you're off by just like 1 or 2 degrees, you don't just get a slightly worse steak. You
Yeah.
basically initiate a completely different chemical
You
reaction.
brain it.
Exactly. The cocoa butter crystallizes all wrong, and your chocolate turns into this chalky mess, or the muscle fibers in that steak just contract so violently that it turns into a rubber tire.
Which is such a great analogy because the margin of error there is just razor thin. I mean, we generally think of heat as this, blunt instrument like a fire.
Yeah.
But in those specific scenarios, it's actually acting as a highly specific catalyst.
Right. And today, for this deep dive, we are taking that exact concept, that microscopic, hyperspecific temperature control, and we're applying it to a completely different
A
frontier.
very different frontier.
Yeah, we are jumping into the world of non-surgical intravaginal radiofrequency treatments. So we're looking at things like Thermiva, Temptur Vitalia, Forma, and BTL Exilis. But we aren't just doing like a surface level read of their marketing brochure.
No, definitely not
We've
that.
got a massive stack of sources today for you. We're talking clinical guidelines, FDA 510K, clearance summaries, actual technical user manuals, and, a lot of peer-reviewed literature.
And our mission today, the thing we're really isolating in this deep dive, is this incredibly specific, almost like a mechanical high wire act.
Yeah.
We are zeroing in on exactly how device operators actively monitor and, more importantly, maintain the exact surface temperatures required to make these intravaginal treatments both safe and effective.
Because, keeping a wand at a precise temperature inside the human body is, it's a lot more complicated than keeping a water bath at 130 degrees for a steak.
Just a little bit, yeah.
Right. So to understand the mechanics of how they actually do this, we really need to start with the baseline of why. Like, why is this exact temperature control the absolute core of the entire procedure?
Right. So for anyone out there who might be dealing with genitourinary syndrome of menopause, or, maybe they're seeking tissue remodeling for mild stress urinary incontinence, the actual therapeutic goal is something called cellular biomodulation.
Cellular biomodulation is
Yeah, it's basically a clinical term for forcing your body's natural regenerative processes out of dormancy.
Oh, interesting.
So when we talk about remodeling vaginal tissue, we're essentially trying to trigger neocollagenesis.
Yeah.
That's the production of brand new collagen and elastin fibers.
Yeah.
And at the same time, you're increasing local blood circulation and regenerating those really small nerve fibers.
Okay, but the sources we looked at made it seem like the cellular machinery that does this, I think they're called fibroblasts. They're incredibly stubborn, right? Like they don't just wake up on their own.
No, they're extremely stubborn. They require a very specific environmental stressor to activate it all.
And that stressor is heat.
Exactly. It's heat, but, and this is the crucial part, it has to fall within this highly restrictive window. This entire healing cascade that we want, it only occurs when the tissue is heated to between 40 degrees Celsius and 45 degrees Celsius.
Wow, so that's just a 5-degree window?
Yeah, a few devices might let operators push up to a ceiling of maybe 47 degrees, but that is the absolute maximum threshold.
Okay, so what actually happens inside that 40 to 45 degree sweet spot?
The physiological response is actually fascinating. When you hit that temperature, the existing collagen triple helix structures
Yeah.
in the tissue, they actually begin to partially uncoil and contract.
Like they're shrinking.
Sort of, yeah.
Mm.
It's this mild thermal trauma. It acts as a cellular siren. It deploys what are known in the body as heat shock proteins.
Okay, let's pause and define those heat shock proteins for you guys listening,
Okay.
because as I was reading the literature, they really seem to be the biological linchpin of this whole thing.
Oh, they entirely are. You can think of heat shock proteins as molecular first responders. So under normal conditions, they're
Yeah.
just chaperones. They basically help other proteins fold correctly.
Hmm.
But the second the tissue hits that specific 40-degree threshold, the sudden thermal stress makes them completely change their function.
Oh, wow.
Yeah, they start signaling to the surrounding cells that there's been an injury, even though the tissue is perfectly intact, and they basically command the fibroblasts to just flood the area with brand new, tightly wound collagen to repair this fake damage.
That is wild. It's like tricking the body into healing itself.
Exactly.
Mhm.
But if you miss that target temperature window,
Yeah.
the whole biological illusion just completely falls apart.
Right, so if the tissue only gets to, say, 38 or 39 degrees.
Then you might deliver a nice, comfortable warming sensation, sure, but you completely fail to recruit those heat shock
The
proteins.
fibroblasts just stay asleep.
They stay dormant, yeah. The treatment becomes entirely ineffective. But then, the other side of that coin is much, much worse.
If you get too hot.
Right. If you breach that 47-degree mark, you cross the line from a controlled therapeutic stressor into just outright thermal damage.
The proteins don't just uncoil, they actually get destroyed.
Yes, they denature completely. So you risk causing severe patient discomfort and, worse, inflicting actual burns on incredibly delicate mucosal tissue.
Which, that brings up a mechanical distinction that I think gets totally lost in the broader conversation about these treatments, because we do see clinical lasers, like CO2 or erbium lasers, used for these exact same issues.
Oh, constantly.
Right. But lasers are ablative. Like, they literally vaporize microscopic collars of tissue. They burn tiny little holes into the mucosal wall to force that wound healing response. But radiofrequency is entirely non-ablative.
Yes, the surface remains completely unbroken.
So how does that change the engineering? Because if you're not burning a hole, how are you getting that heat deep into the tissue?
It changes the entire engineering approach. A laser, is delivering concentrated light energy to instantaneously vaporize water in the tissue from the outside in.
Yeah.
Radiofrequency doesn't do that at all. In fact, the RF wand itself isn't even generating heat on its surface. It's not like a hot curling iron that you press against the skin.
Okay, wait. This is where the physics of it just broke my brain a little bit when I was reading the manuals. If the wand itself isn't hot, how on earth is it elevating the vaginal tissue to 45 degrees?
I know, it's counterintuitive. The device is actually acting as a conduit for controlled electromagnetic waves.
Okay.
So when this specific frequency of electrical energy penetrates the mucosa, it interacts directly with the intracellular ions and the water molecules that are residing deep down in the connective tissues.
So it's passing through the surface to get to the water underneath.
Exactly. And the alternating current essentially forces these charged particles and the polar water molecules to just rapidly oscillate.
So it's like a microscopic game of molecular bumper cars.
That is exactly what it is. The energy causes these molecules to vibrate, literally millions of times a second. They just continuously smash into one another. And that intense high-speed friction is what actually generates the heat.
So the tissue is literally heating itself from the inside out.
Yes, and that bumper car analogy really highlights the core engineering challenge here. Because the thermal effect is happening deeper down in the vaginal wall architecture, the surface mucosa can stay intact, which is great. But it also means the heat is radiating outward toward the wand rather than inward from the wand.
Oh, I see. And that makes hitting that 40 to 45 degree window incredibly precarious. Because if the heat is being generated internally through molecular friction, the human operator holding the device is completely blind to it.
Completely blind.
The clinician physically cannot feel the difference between a therapeutic 44 degrees and a dangerous 47 degrees through the plastic casing of a medical handpiece.
No, the margin of error is way too narrow for human sensation. So the physical devices themselves have to step in and act as these highly advanced real-time thermal mappers.
Okay, let's dive into the hardware that actually makes that possible. Looking at the FDA 510K clearance summaries for devices like the Temperature Vitalia, the level of diagnostic tech packed into the tiny tip of these probes is just staggering.
It really is. It is not just a dumb electrode emitting a current.
Right.
Devices of this caliber employ something called dual temperature sensing. So instead of relying on just a single thermometer, which, might malfunction or give a weird localized reading, they embed multiple thermistors directly into the active tip of the electrode.
Right, at the point of contact.
Exactly, at the precise anatomical point of contact with the patient.
And these thermistors are basically creating this continuous closed-loop feedback system with the main generator, right? They're updating the system on the surface temperature fractions of a second at a time.
Yes. And the bench testing detailed in those FDA summaries really underscores how rigorous this feedback loop actually has to be to get clearance. The manufacturer didn't just test the wands against, standard digital thermometers.
What did they use?
They actually benchmarked the internal thermistor readings against a FLIR thermal camera system.
Wait, really? A FLIR system, like the gold standard infrared cameras?
Yep. FLIR maps heat signatures with extreme sensitivity. So in a clinical testing environment, they're analyzing the exact heat bloom on the tissue surface, and they're comparing it to what the wand claims it's reading internally.
That is wild. And what were the results?
The data showed an incredibly tight correlation. Over sustained 10-minute treatment intervals, the average delta, so the difference between the highly sensitive thermal camera and the handpiece's own internal reading was just plus or minus 1.5 degrees Celsius.
Wow. So that plus or minus 1.5-degree margin is essentially the technological safety net.
Exactly.
Mhm.
It confirms the hardware can read the environment accurately enough to keep the patient just below that 47-degree danger zone, all while sustaining the cellular biomodulation cascade.
Okay, but reading the temperature accurately really only solves half the physics problem, doesn't it? Because we are still dealing with raw electrical current moving through a highly conductive, very wet mucosal environment.
Oh, yeah. That is a massive variable.
Right. It's human error mixed with physical contact. Because if an operator is moving this wand around inside the vaginal canal and they accidentally lift the tip slightly, or maybe the conductive gel thins out that electrical circuit is broken,
And that's dangerous.
because you're shooting electromagnetic energy into the body. If the contact isn't flush, that energy is just going to arc, right? It'll create a literal spark that can instantly burn the tissue.
Yes. The risk of arcing in a mucosal cavity is very significant, which is why the technical manuals outline a secondary, entirely separate hardware safeguard, which is called impedance monitoring.
Okay, let's break down how impedance functions in this specific context, because the user manuals we read were heavily focused on it.
Basically, impedance is simply the measure of electrical resistance. Different materials resist the flow of electrical current at different rates. Air has massive resistance. Conductive surgical gel has very little.
And human vaginal mucosa.
It falls into a very predictable, highly specific range of resistance.
Okay, so according to the Thermiva user manual, the main generator is constantly interrogating the tissue with this tiny, imperceptible current to calculate this resistance, which is measured in ohms.
Right.
And the device is strictly coded to require a reading between 80 and 599 ohms.
Exactly. So when the radio frequency electrode is resting perfectly flush against the mucosal wall and it's surrounded by the proper amount of conductive medium, the electrical resistance falls perfectly into that 80 to 599 ohm sweet spot.
It knows the circuit is secure.
The machine knows it's safe. But the very millisecond the operator's hand slips or the wand loses full contact and introduces an air gap.
The resistance spikes wildly out of that range.
Yes. And when that impedance spike hits the generator, the software responds instantaneously, just cuts the radio frequency power completely.
It just shuts down.
The machine will simply refuse to deliver energy unless it can confirm literally thousands of times per second that the impedance indicates safe, flush contact. It physically prevents an arc before it even has time to fully form.
It is a built-in failsafe governing the literal physics of the room. The thermistors manage the thermodynamics, and the impedance monitor manages the electrical conductivity.
Exactly. But as amazing as all this sophisticated hardware is, it's effectively useless without the human operator orchestrating it in real time.
Right, because this brings us to the transition from the engineering of the wand to the actual reality of the clinical environment. Because this is not a passive treatment, you know? It's not a tanning bed where a patient is placed inside machine and left alone for 20 minutes.
No, not at all. It is a highly active, continuous dialogue between the clinician's physical movements and the machine's software feedback.
Yeah, looking at the procedural guidelines for Thermiva, it gives a really clear picture of the cognitive load that is placed on the provider during like a typical 15 to 30-minute session, because the operator is managing a graphical user interface, basically a clinical touchscreen that presents a constant stream of real-time data.
And that interface heavily features two primary metrics. First, the provider inputs a set temp, which acts as the treatment goal. The guidelines generally recommend setting this initial target at 45 degrees Celsius for internal remodeling,
Right.
and then directly adjacent to that on the screen is the actual temp, or ACT temp, which is the live feed from those dual thermistors at the tip.
And the challenge here is that the operator cannot simply press the wand against a section of tissue and just hold it there until the actual temp reaches the set temp.
Oh, absolutely not. If they left the electrode stationary, the molecular friction would pool in one localized spot. You would rapidly overshoot the 47-degree threshold and cause a severe burn long before the heat could dissipate into the surrounding tissue.
Right. So the procedural guidelines strictly dictate that the active tip has to remain in constant slow motion. The clinician is performing this sweeping technique, constantly varying their depth and the lines they are drawing across the tissue, ensuring they never trace the exact same path consecutively without letting it cool briefly.
It is an incredibly demanding task. I mean, think about it. You are asking a provider to maintain a constant, steady, sweeping motion inside a confined anatomical space while simultaneously watching a screen to ensure the actual temperature stays within a microscopic 3-degree margin of the target.
It sounds a lot like driving a manual transmission car, feathering the clutch, and staring at the speedometer to maintain exactly 45 miles an hour, all while navigating a really winding road.
That's a perfect way to describe it.
Yeah.
And the visual distraction alone could compromise patient safety. You can't just stare at a screen.
Right, so to mitigate this cognitive load, the manufacturers actually incorporate auditory sensory aids into the software. The operator doesn't have to stare unblinkingly at the actual temperature readout.
No, the device emits a distinct audible beep every 5 seconds.
And that beep is essentially a system-wide confirmation. It tells the provider, without them ever having to look away from the patient, that the impedance is within that safe 80 to 599 ohm range, the energy is actively flowing, and the thermistors confirm the tissue is approaching the therapeutic window.
It creates a physical rhythm for the procedure. The clinician can pace their sweeping motions to the cadence of the audio feedback. Wow. And furthermore, the guidelines are absolute on one specific operational rule. The operator must never withdraw the electrode from contact with the tissue while the energy is active.
Even with the microsecond impedance shutoff.
Even with that failsafe, you do not test the failsafe unnecessarily. The protocol is always to disengage the foot pedal first, cut the energy, and then remove the wand.
Okay, but this constant sweeping motion introduces a massive logistical flaw regarding the cellular biomodulation we discussed earlier. Because if the wand is constantly moving across different patches of tissue, the surface temperature is naturally going to ebb and flow, right?
Yeah, naturally.
It might peak at 45 degrees in one area, but as the operator sweeps to a cooler zone, the local temperature drops to 42, then maybe down to 39 degrees before heating back up on the next pass.
That fluctuation is just an inherent byproduct of the required safety motion. You can't avoid it.
So, if that's true, how does a clinician guarantee that a patient is actually receiving a full therapeutic dose? Like, if a protocol dictates 15 minutes of treatment, but the tissue was dipping below 40 degrees for half of that time because the operator was sweeping slightly too fast, the patient isn't getting 15 minutes of neocollagenesis.
Right. They're getting 7 minutes of therapy and 8 minutes of really expensive warmth.
Exactly. So how do they fix that?
This is perhaps one of the most elegant software solutions detailed in the technical documents, specifically highlighted in the temperature vitalia manuals. The engineers recognized that human variability in hand speed would compromise clinical outcomes.
So how did they code around the human element?
They completely decoupled the treatment timer from the actual time elapsed in the room.
Decoupled it how?
So, when the clinician steps on the pedal to begin a 15-minute session, the timer on the interface does not immediately begin counting down. The internal software only activates the timer when the thermistors confirm that the target tissue has successfully breached the therapeutic threshold of 40 degrees.
Oh, wow. That fundamentally changes the procedure.
It entirely changes it. If the operator speeds up their sweeping motion and the local tissue temperature drops to 39 degrees, the countdown timer instantly pauses.
It just waits.
It waits. It only records the cumulative seconds and minutes that the tissue spends actively dwelling within that precise cellular biomodulation window.
That is brilliant. It entirely removes the clinical guesswork. The operator doesn't have to manually estimate the cumulative time spent at the target temperature. The machine dictates the endpoint.
Yes. If the clinical protocol prescribes 15 minutes of therapeutic heat, the patient remains in the chair until the software verifies literally second by second that exactly 15 minutes of structural protein alteration has occurred.
So it guarantees that the biological stimulus is completely standardized, regardless of whether an operator's hand speed varies from, Tuesday to Thursday, or if one patient's tissue has higher initial resistance than another's.
The total therapeutic thermal dose delivered remains mathematically consistent every single time.
Which brings us to a really critical realization for you, the listener, regarding how this technology is currently being marketed to consumers. Because we have spent this entire deep dive unpacking the highly engineered safety net required to vibrate water molecules safely, right?
A massive safety net.
We're talking dual thermistors, the FLIR validated accuracy, the microsecond impedance shutoffs, and those temperature-gated software timers.
And understanding that intricate triad of safety, the hardware, the software, and the trained human operator, it completely reframes how consumers must view the current influx of consumer-grade radiofrequency devices on the market.
Because if you browse online right now, you will find dozens of inexpensive at-home RF wands claiming to treat the exact same indications: menopause symptoms, vaginal laxity, incontinence, and they market themselves as a really convenient, cost-effective alternative to clinical treatments.
But when you apply the mechanical realities we've just discussed to those $200 consumer devices, the engineering impossibility becomes glaringly obvious. The clinical literature states plainly that home-use RF devices cannot reach the necessary dermal temperatures to induce actual collagen remodeling.
And, the assumption is usually just that they have smaller batteries or maybe weaker generators, but it's much deeper than that, isn't it?
It's an issue of validated thermal feedback. Integrating clinical-grade dual thermistors and high-frequency impedance monitoring circuits into a consumer device is financially and technologically unfeasible.
And without those specific safeguards, an at-home device is basically trapped in an engineering paradox.
Exactly. Without real-time impedance monitoring to instantly cut power when the user inevitably alters their contact angle, and without precision thermistors feeding into a GUI that forces a pause in the timer, the device manufacturer has to make a choice.
What's the choice?
They must artificially cap the energy output so low that it physically cannot reach 40 degrees, rendering it biologically useless for neocollagenesis.
Or, conversely, if they do allow the device to generate enough electromagnetic energy to actually reach 45 degrees, they are placing a live tissue heating current into the hands of an untrained consumer without the automated microsecond safety shutoffs.
And that scenario guarantees severe internal burns. There is no middle ground.
Right. The professional devices are FDA cleared specifically because they rely on that continuous data loop to prevent disaster. You simply cannot replicate the physics, the fail-safes, and the operator technique in your bathroom.
You really can't.
So if you are exploring these treatments, maybe you are navigating the physiological changes of menopause, or you're seeking a non-surgical option for pelvic floor laxity, the mechanics essentially dictate your path. A clinical setting isn't just a luxury upcharge, it is an absolute baseline requirement for reproducible, safe, evidence-based outcomes.
Because you aren't just paying for access to radio frequency waves, you are paying for the micromanaged orchestration of those waves.
It is the precise control of time, temperature, and technique that transforms a potentially dangerous electrical current into a highly targeted regenerative therapy.
Exactly.
So we have traced the journey of this tech all the way from the friction of oscillating intracellular ions up through the impedance monitors preventing electrical arcs, all the way to the software algorithms that guarantee your clinical dose. We've seen how localized thermal mapping can safely remodel incredibly delicate mucosal tissue entirely from the inside out without a single ablative cut.
And that success, it actually raises a really provocative question for the future of internal medicine as a whole.
Oh, where do you see it going?
Well, we've proven that this technology can track and sustain thermal energy with millimeter precision to remodel vaginal mucosa. Considering this capability, it is highly probable that this exact non-ablative thermal tracking technology, the combination of microthermistors and impedance monitoring, could soon be miniaturized even further.
Wait, how far could they take it? Are we talking about like swallowable diagnostics?
More likely delivery via a specialized endoscope. Imagine applying this exact same precise RF control to treat other internal mucosal issues throughout the human body.
Oh, wow.
Clinicians could potentially use miniaturized RF wands to gently remodel and repair internal scar tissue resulting from previous abdominal surgeries, or maybe to treat painful gastrointestinal strictures.
Taking the technology that revitalizes pelvic floor connective tissue and adapting it to dissolve surgical adhesions in the gut.
Exactly. They could induce that exact same targeted cellular biomodulation to heal damaged tissue from the inside out, guided entirely by thermal feedback screens, without ever needing a scalpel.
The ability to manipulate the body's own healing cascade at a molecular level, governed by just brilliant hardware, is a frontier that is truly just beginning to open up.
The applications for energy-based internal healing are vast, provided we maintain the exact same reverence for the mechanics of temperature control.
Well, we hope this deep dive gave you some serious aha moments about the hidden physics and engineering happening inside the clinic. Remember, whether it is tempering chocolate in your kitchen or regenerating collagen at a cellular level, temperature is everything. Keep learning, keep asking questions, and we'll catch you on the next deep dive.